So this is strong and efficient consistency with consistency-aware durability from last year. And in this paper, they make a couple of claims. They're really the core of this paper is cross-client monotonic reads, which is a novel and strong consistency property. It's kind of like monotonic reads in session guarantees, which we're more used to. But in this case, you don't have to use the same client or you don't have to be in the same session in order to get the monotonic reads property. It's weaker than linearizability. You can read stale values. Read your writes is not guaranteed, but they claim that this is still a useful consistency property for applications. And it's more performant than linearizability. And they outline a system in this paper called consistency-aware durability, or CAD, which guarantees cross-client monotonic reads. So the property monotonic reads just means that every time the system satisfies a query, the value that it returns is at least as fresh as the one returned by the previous query to any client. And we'll spend the rest of the talk talking about CAD, which is the system that they implement to efficiently obey this cross-client monotonic reads property. So let's take an example with 5 servers. We're going to need a leader, so we'll say S1 is the leader. CAD works with leader-based consensus protocols. In this paper, they're using ZAB, the ZooKeeper Atomic Broadcast Protocol, but it could just as well be Paxos or Raft. I don't see anything ZAB specific about their technique here. So with a leader-based protocol, all of the writes go to the leader. So we're going to write some value A1 to a key A, and S1 appends it to its log. And eventually this update is replicated to all of the followers. This system is a key value store, and I'm going to kind of pretend that there's only one key in the system called A, but from time to time I'll mention how this generalizes to multiple keys. So we've written A1, we've replicated it to all the followers, and let's say that we write to the leader again and we update the same key. The leader then appends it to its log after the first log entry. So let's look at this situation. We've got the leader has 2 log entries, and then all the followers only have 1 log entry. What reads are permitted in this situation that would be monotonic? Clearly, you can read from the leader, and the leader can just return the latest value. So that will always be at least as fresh as the last value that the leader returned. So reading from the leader is monotonic. But follower reads, that's where things really get complicated. Let's consider first what happens if you read from the leader and then read from the follower. So if you read from the leader and it returns the latest value, and then you read from a follower and it doesn't know the latest value, so it returns a more stale value, that's obviously not monotonic. You're going back in time. And this is where the protocol from this paper, consistency-aware durability, where it comes in. In CAD, we've got this idea of a durable index. The leader keeps track of this index, and it's the log entry that all of the followers have replicated. The leader keeps track of how recently each of the keys was updated, and it also keeps track of the durable index, so it knows whether some keys, their latest updates are durable, and then some keys, like A here, their latest update is not yet durable. So in CAD, when the leader receives a read request for a key, like A, that is not yet durable, so A2 has not been fully replicated yet, the leader does not reply. Instead, it awaits replication to all of the followers. Then it updates the durable index. Now the durable index is past the latest update to A, and so the leader can respond with the latest value of A. And now the cool thing is that any client can read from any member of the set at this point, and you will always get a value of A2 or more recent than that. So this is how CAD enforces monotonic reads using the durable index. And we can go through the same sequence here for 2 follower reads in a row. This is the example I just showed you is from the paper. The next example that I'm going to show is not from the paper, but I think I got it right. And I really wanted to work through this one to fully understand it. So we're going to start off the same where we write A2 to the leader. But this time, let's say that the leader replicates to 2 of the followers, but the other 2 followers are still lagging. And now instead of reading from the leader, we're going to do 2 follower reads. So first we read from an up-to-date follower. And if it were not for CAD, let's say that the follower just responded with the latest value. And then we could read from a different laggy follower and get a more stale value. And so this would not be monotonic. We're going back in time. So let's see how the durable index solves this problem for 2 follower reads. So we start off, the durable index is at the first log entry. We write A2, replicated to 2 of the followers. The other 2 followers don't have it yet. Now notice, A2 is durable, you might say, because it's been replicated to a majority, but it hasn't been replicated to all of the members. And so the durable index is not advanced. In CAD, the durable index doesn't advance until all of the members replicate. So now, when you read from S2 like before, S2 sees that it's got a more recent version of A than the durable index, right? S2's value is A2, but the durable index is still at A1. The servers, by the way, the followers learn the durable index from heartbeats from the leader. So S2 knows that it's got a too fresh value of A that is not yet durable. So what it does in this case is that it forwards the query to the leader. The leader now waits, and it awaits replication to the entire set. Only after this can the leader move the durable index, and now its latest value is durable, and so it can reply, and then S2 forwards that reply back to the follower. And then once again, we're safe. We can read from any of the followers, and they will reply with the durable value, and so this is once again monotonic. So that's how CAD works for both leader reads and follower reads and combinations of follower reads. My interpretation of how this system works could be wrong. I could be missing some subtleties, but it seems to me that the system presents a consistent snapshot of the data at the durable index. And the durable index can only move forward. And so that's how it ensures a monotonically increasing view of the data over time without any sessions. Any read of a key's version that is after the durable index waits on the server until the durable index advances to cover that version. And if you do a follower read, the follower might be stale, and so the follower might have a key version before the durable index. In that case, it also awaits in advance of the durable index. So far so good. We've sort of proven to ourselves that by advancing the durable index only when all followers replicate every change, we can get cross-client monotonic consistency. But waiting for all followers is very expensive. It means that if there's even one very laggy or completely offline follower, then all reads will have to go to the primary, and they'll all block waiting for the primary to update the durable index. So is there some way to get a compromise here where we still get cross-client monotonic reads, but we don't suffer if there's just one or two laggy members? So CAD has a sense of an active set here. Instead of requiring all members to replicate an update before we can advance the durable index, we define this active set. It has to be at least a majority, because replicating to the active set has to mean that your data is durable to minority losses. But we can exclude laggy nodes, like S4 and S5 here are not members of the active set. And that means that the durable index is as up to date as the active set has replicated. If we write a value to the leader and the leader replicates it to all of the members of the active set, then the leader can advance the durable index before it has replicated to the other followers. Now, if you do a read request to a member of the active set, then the active set's view of the durable index is kept up to date. And in this case, the follower can respond right away with its version of the value without forwarding to the leader. If we try to read from a member that's not part of the active set, the paper doesn't actually say exactly what happens here. It just says that it's prohibited. I think it would be reasonable for this member to forward to the leader, or try to if it's not partitioned, and then forward the leader's reply. And then this would also be monotonic. So I think that's pretty clever. They maintain the active set using timed leases. And there's some careful discussion about clocks and timing. And what they need to do is ensure that a member knows that it is not part of the active set and takes itself out of the active set before the leader knows that. And as long as that sequence is maintained, then the system can provide monotonic reads. So that's it for the algorithm. Let's take a look at their claims once more. So they said cross-client monotonic reads is a novel and strong consistency property. I'll say sure, it's sort of semantics. It does at least seem unusual, but I'm not sure I would call it strong, since it doesn't even include read your writes. They say it's weaker than linearizability, but still useful to applications. And this usefulness I'm kind of skeptical of. I feel like if you can't read your writes, why not just go for eventual consistency? Do you care about consistency at all? They provide a few example applications, but I didn't find them very persuasive. I thought that there might be less exotic ways to support the applications that they propose. And I kind of wondered, if it is a novel property, that actually makes it less likely that it's useful, because developers have a hard enough time already with the well-known consistency levels that are well documented and that have whole libraries are built with the assumption that a system might be linearizable or might be eventually consistent. If you introduce a new consistency level, it might be rather hard to adapt applications to actually use it. I think of a better example, which would be if you had read-only queries with foreign key relations. So imagine that you've got two applications and one of them is only writing. And as it's writing, it maintains foreign key relations. So first it inserts a record and then it inserts another record that refers to it in that order. And then you have a read-only application that is reading from the store, assuming that these foreign key relations are always obeyed. Then in that case, monotonicity might be a useful property, even without read your writes. But since writes in this system are not reliable, you can lose writes due to a failover. That means that that the application that's writing might not actually be able to maintain those foreign key constraints anyway. So I admit I'm a little bit stumped. I'm not sure which application would really benefit from this new consistency property. They say that it's more performant than linearizability, and this seems to be true. Writes are definitely faster because they don't wait for any acknowledgement, much less durability. MongoDB used to have unacknowledged writes by default, and this turned out to be not the right choice. So we moved to leader acknowledged writes, and pretty soon we're probably going to move to durable writes by default. But they are slower, so this is more performant than linearizability. Reads in this system are faster than linearizable reads because there's no consensus step. If you are mostly reading keys that have not recently been updated, if you are reading keys that have been recently updated, then each read will have to wait for the active set to replicate the latest version of that key. And so in that case, you'll end up being basically linearizable anyway. And the charts that they show in their evaluation show this, that if you are reading infrequently updated data, then you get the same performance as eventual consistency. But if your access pattern is different, if you're constantly writing and then reading the same keys, then you end up having similar performance to a linearizable system. Finally, they claim that their system guarantees cross-client monotonic reads. That looks correct to me, and they include a proof in the paper. I would say that since the follower redirects reads to the leader, if the follower is not in the active set or doesn't have the last durable version of a value, then follower reads are safe, and also leader reads are safe because the leader awaits durability. It will never return a value that can be rolled back. So their conclusion is that cross-client monotonic reads, a strong consistency guarantee, can be realized efficiently upon CAD. When enabling stronger consistency, CAD may not be suitable for a few applications that cannot tolerate any data loss. However, it offers a new useful middle ground for many systems that currently use asynchronous durability to realize stronger semantics without compromising on performance. I think that the most ambiguous claim here is that this is a useful middle ground. My conclusion reading this paper is that cross-client monotonic reads are definitely easier to work with than session-based monotonic reads. We've talked about this in this group before, but session-based guarantees, like causal consistency with sessions, it's pretty easy to implement, but it's very hard to use by multi-tier application architectures because there it tends to be that the layer that talks to the database, it gets some query result, which then bubbles up through the layers. And then the top layer might follow that up with a second query that bubbles back down through the layers. But by that point, the original session has been lost. Session management is at a different layer from the layer that's generating the queries. And so taking advantage of session guarantees is actually very hard for a lot of applications. Making monotonicity cross-client does seem like an advancement. But I think that any consistency level that doesn't have read your writes is going to be pretty niche. Developers tend to get confused if they do something like insert a key into a list and then they check the length of the list and their insert has not taken effect yet. Since this is a pretty niche property, I think that cross-client monotonic reads are useful only as an addition to a system that already has a variety of consistent choices. If I were building a database from scratch, I would provide other consistency guarantees first. I would give clients the option of using linearizable or a snapshot or causal consistency or eventually consistent. Any of those, I think, is easier to understand and more applicable than cross-client monotonic reads. But if I did decide to add this property, then I do think that CAD is a clever way to guarantee it. And as far as I can tell, it's sort of bolt-on. You could add CAD to a system that implements other consistency levels. You could provide cross-client monotonic reads as an option and bolt on CAD as a way to implement it. And that's it. That's my presentation. Thanks.